Hi, I'm Shichana and I'm a PhD student at University College Dublin. I'll be presenting our full paper DeepQPP, a pairwise interaction-based deep learning model for supervised query performance prediction on behalf of all my co-authors, Debashish Ganguly from University of Glasgow, Derek Green from University College Dublin, and Mandar Mitra from Indian Statistical Institute. So this is kind of the brief overview of this presentation. Firstly, I'll talk about what is QPP and why do we need this. Next, we will see how we developed QPP with neural models where I explain our proposed model DeepQPP. And then I'll show you the architecture of it. And lastly, we'll see the overall performance of this model compared to others. Okay, so what is QPP? I would like to quote from the paper published in 2010, where authors say that if we could determine in advance which retrieval model would work well for a given query, then hopefully selecting the appropriate retrieval model on a per query basis could improve the retrieval effectiveness significantly. So, in other words, the objective of QPP would be to predict how easy or difficult a given query is for an IO system. So, what do we mean by an easy or difficult query? So, let's explain the situation like this. Assume that an user is given three different retrieval models, as you can see here, and the user wants to know who would give more relevant documents for the input query that the user has. Let's say there are two queries, agoraphobia, and the other one is black bear attacks. Since the first query is about a disease, we could assume that the relevant document set would be quite distinct, or rather, we could say it's separable from the whole collection. On the other hand, black bear attacks is more of a subtle query. That is, there could be plenty of context which might not satisfy users' specific information need. So, in that case, user might want to reformulate the query, reformulate the input query to experience a better outcome. So there should be a way to measure this query specificity, and this is where the QPP estimator comes into play. It will tell the user that whether the input query is specific or not. So the QPP estimator gives an estimation to the user how easy or difficult the input query is, and based on that, it helps the user to identify whether the user needs to reformulate the query or not. And there are two different situations where we use these QPP estimators. Firstly, in pre-retrieval situation where you have the query, you predict the performance of each query based on the content and the context of the query, and then you rank the queries based on their specificity, that is whether it is easy or difficult. Average IDF, max IDF, these are the pre-retrieval estimators. And next we have the post-retrieval situations where you have the query and you estimate the query performance by analyzing the result list returned by the retrieval engine. And then you rank the queries. Clarity, WIG, NQC, these are such post-retrieval estimators. Now uh, let's move on to the architecture of our model, the whole description of the model rather. We see the benefits of using supervised approaches that has predominantly been established for ranking and recommendation tasks very lately. And the exploration of supervised approaches for QPP has been limited. And with this motivation, we present here a supervised end-to-end neural approach for query performance prediction. So in contrast to unsupervised approaches, where we rely on mainly various statistics of document score distributions, here in DeepQPP, our approach is entirely data-driven. So in terms of novelty, there are two aspects of this work. First, it is an end-to-end supervised QPP model where instead of learning to optimize the relative importance of different predictors, our model learns a comparison function of relative specificity between query pairs. And secondly, it uses early interactions between query document pairs, where, uh, as you see, where our model makes use of early interactions between a query and its top retrieved set of documents. And we argue that this way of constituting the query improves the model's capacity to generalize better as compared to the late interaction between the content of the queries and the documents. So, before we discuss the working principle of our proposed model, let me just remind you of the fundamental difference between a interaction based model, representation based model, and an interaction based model. So, in case of representation, it constructs a representation of each instance from a pair of inputs and then optimizes the representation so that it can maximize the likelihood of predicting a function involving this pair. On the other hand, in case of interaction-based model, it first transforms a paired data instance into a single instance via an interaction operator. So now let's look inside our model and how it works. So unlike the entirely representation-based or interaction-based model, our model basically combines the benefits of both early and late interactions. And it addresses two things. Firstly, the interaction of the terms in the top retrieved documents of a query with the constituent terms of the query itself. And secondly, it identifies the characteristic pattern of these interactions to estimate the comparison function between a pair of queries. As you can see here, each individual query document interaction is shown in a different color. Uh, so this is the entire architecture. The entire end-to-end architecture of our proposed QPP system. You see here, it comprises a Siamese network of shared parameters of layered convolution feature extraction. And then we have uh, two options here. One is entirely you merge or concatenate and pass through a fully connected layer and a sigmoid loss for pairwise testing, as you see here, and it gives you a binary comparison indicator between a pair. Or there is other option where you have a linear activation layer with pairwise hinge loss for pointwise testing and produces a score for a given query. One point to be noted here that point to be noted here is obviously there are a number of different choices for slicing up the interaction tensor here into a set of matrices for the purpose of separately applying 2D convolution on each and then combining the features. You could find all such variations in detail in the paper. Okay, so we experimented with two standard ad hoc IO test collections. One is Trek Robust, as you can see here, which is comprised of news articles, and the ClueWeb09B. It has crawled web pages. For the ClueWeb experiments, we use the Waterloo spam scores to remove spam documents. Please read through our paper for more details on experiments. And this table represents the QPP results for all the methods investigated. We depict a comparison of the QPP effectiveness between our proposed model DeepQPP and a set of unsupervised methods that is in the first group, that is Clarity and QCWIG and EVF, and a set of supervised baselines in the second group. And we observed that the average accuracy and the correlation values of our proposed model over the best performing baseline, which is this WS near QPP, are statistically significant with over 97% confidence. For more observations, please go through our paper. Thank you. Thanks for being patient.